Okay, thank you very much, Laurent, for a nice introduction. I would like to start by highlighting the fact that our work on silicon nitride surface grating couplers was realized in a relatively wide international collaborations, which includes the Institute CA-Leti and Centre de Nanoscience and Nanotechnology in France, Carleton University and National Research Council in Canada, and also University of Southampton in United Kingdom. I also would like to highlight that the main work on this kind of surface grating couplers in silicon nitride was mainly done by our PhD student, William Fraser, which is from Carleton University in Canada, and my former PhD student, Radovan Korček, who is recently a postdoc in NRC Canada. So we can start. We know that integrated photonics is a very promising technology, providing very wide impact for the future and for our modern society. Integrated photonics enables realization of complex and also compact devices with high performances in order to create a complete optical system which can be integrated directly on the chip. Integrated photonics also offer many advantages such as scalability, performance enhancements, dense integration, device miniaturization, and also relatively nice power efficiency. Over the last decades, the scope of integrated photonics has significantly expanded, especially due to the progress of silicon-based material platforms, namely both platforms, silicon on insulator and silicon nitride. Both platforms can provide many distinctive advantages for photonic integration, which includes wide spectral coverage, fabrication, maturity, advanced integration, and also open access to photonic foundries in order to achieve rapid chip prototyping and ensuring compatibility with CMOS fabrication technology. All of these benefits can be then leveraged for many emerging applications, which nowadays includes data centers, communications, interconnects, or even optical computing, to name a few. On the other hand, however, these platforms are excellent for development of passive devices. Unfortunately, both platforms have indirect bandgap materials, which means they cannot light cannot be directly generated on a chip, but the light need to be delivered to the chip from the external resources. To ensure a successful practical implementation of silicon photonics solution, large-scale photonic system require to have efficient connections between optical devices on a chip and also out of the chip. So from this reason, optical coupling between integrated waveguides and outside world is still a real challenge in the field of integrated photonics. Optical coupling is mainly restricted or limited by the geometrical, material, and modal mismatches between two different worlds. A direct connection between the integrated optical waveguides and optical fibers is typically very lossy, achieving losses about minus 30 dB. This essentially means that less than 1% of the optical power can be efficiently coupled to the waveguide or from the waveguide, which is simply not very practical for many applications. To address this problem, there are edge couplers and surface grating couplers that are typically used to develop high-performance optical input and output coupling interfaces. Fiber chip edge couplers can offer low loss, a wideband operation with a polarization insensitivity. Unfortunately, they can be located only on the chip edge, which limits the design flexibility of the photonic integrated circuits. Typically, edge couplers are also connected with lensed optical fibers or optical fibers with high numerical aperture. If we want to connect edge couplers with regular SMF28 optical fibers, we need to adapt complex design of the devices, and additional fabrication steps needs to be realized. So, on the other hand, we have surface grating couplers that can be positioned at arbitrary location on a chip surface, which can provide a desired accessibility for a chip design and device testing, dice testing and also the wafer scale characterization. Grating couplers are therefore suitable for high-density optical interconnects and also enable realization of multi-port, free space, or fiber-coupled optical interfaces, which can support integration through optical interposers or support application in free space or optical communications. The operation of surface grating couplers is governed by the phase matching condition, which essentially couples and relates the geometrical parameters of the structure with the operating condition we want to explore. The performance of surface grating couplers is defined through three different parameters, which is scattering efficiency, mode matching efficiency, and radiation efficiency. Radiation efficiency, also called grating directionality. Jointly, we characterize the performance of grating couplers by coupling losses or coupling efficiency. So, in the next part of my presentation, I will provide an overview of our recent results we obtained in the development of surface grating couplers that are realized either on native or hybrid silicon nitride waveguides, and they are engineered with subwavelength grating metamaterials. So in the first step in our work, we focuses on the development of simple native surface grating couplers on silicon nitride. The initial work was done in collaboration with Center de Nanoscience and Nanotechnology. We use LPCVD silicon nitride wafers from CA-Leti, and the fabrication was done in the Siduzen Institute in Paris. So for the uniform grating couplers, we experimentally measured coupling efficiency of about minus 3.9 dB, which is only 0.3 dB higher compared to our nominal FDTD predictions. Besides this single hero demonstration, we also observe that this kind of grating couplers are quite tolerant to the presence of fabrication imperfection, and for some geometrical variation, what we explore on the chip, for a geometry variation of about plus minus 40 nanometer, the coupling loss remains relatively low, with the values between 0.3 and 0.6 dB. The further enhancement of the performance for this kind of surface grating couplers was achieved by grating apodization, in this case by duty cycle apodization. The fabricated grating couplers have coupling efficiency of about minus 3 dB, with a very low coupling loss penalty, again, of only 0.2 dB, which very well aligns with our FDTD calculation. In the next step in our work, we our design were also validated using open access foundry prototyping services. This was done in collaboration with the Canadian company Applied Nanotools. As you can see on these slides, we achieved very nice results for different operating conditions, different polarization calculation. In the next step in our work, we our design were also validated using open access foundry prototyping services. This was done in collaboration with the Canadian company Applied Nanotools. As you can see on these slides, we achieved very nice results for different operating conditions, different polarization states, and there is also a very nice agreement between the design prediction and experimental results. Albeit, although these results are quite nice and promising, this kind of grating couplers are kind of limited by the number of parameters we can optimize, which in turn limits the performance of this kind of surface grating couplers. Especially these kind of devices are limited by the weak radiation from the grating and poor overlap between the out-radiated grating field and the near Gaussian optical fiber mode. So, in order to address this problem, we introduce subwavelength metamaterials. As we know, metamaterial integrated photonics took a massive leap in the field of integrated photonics since the first demonstration of SWG materials in silicon waveguide. SWG materials become essential design tool to improve the performance of many photonic integrated devices. So in terms of surface grating couplers, we can efficiently engineer their efficiency, their polarization and sensitivity, and also we can achieve much better performance in terms of broadband operation. Recently, it was also demonstrated that utilization of subwavelength metamaterials is very promising also for silicon nitride integrated photonics. People from McMaster University in collaboration with NRC demonstrated a couple of SWG engineered devices in silicon nitride waveguides, for instance, low-loss spirals with losses about 1.3 dB and 1.8 dB for TE and TM polarization, and also the same group of people demonstrated very high Q resonators which are built on subwavelength metamaterials in silicon nitride. So we also exploit these SWG metamaterials in our silicon nitride surface grating couplers. We design fabricated uniform silicon nitride grating couplers, and as we can expect from our calculation, the performance is lower compared to the regular silicon nitride grating couplers, which is attributed to the reduced strength of the grating. On the other hand, we have additional degree of freedom to modify the strength and potentially optimize the performance of the surface grating couplers. The measured peak coupling efficiency ranges between minus 4.4 and minus 4.6 dB, and also the alignment and matching between the design and the experiment was quite nice. So in the next step in our work, we design metamaterial apodized surface grating couplers with a focalized geometry, as we can see on the following figure. The operation of this grating coupler leverages two key design principles or two key design steps. We engineer the grating strength locally, which is controlled by combination of SWG and duty cycle apodization along the light propagation direction to achieve near Gaussian profile of the outradiated grating field. And the second step, the diffracted light has a convergence phase front that helps to focalize beam to the fiber, which is positioned above the grating. With this, we can optimize the performance of the grating coupler, especially in terms of improved optical field overlap in the near field, and by positioning the fiber above the chip, we can significantly improve the overall performance of our devices. In terms of coupling performance, coupling efficiencies of about minus 1.6 dB and minus 2 dB are predicted by our FDTD simulation for C-band and O-band surface grating couplers. Compared to the conventional surface grating couplers, we can see that this is improvement of more than 2 dB per coupler, which is quite nice achievement. In collaboration with Applied Nanotools, this kind of surface grating couplers were fabricated considering the minimum feature size of the process, which was said to be larger than 120 nanometer in order to assure compatibility with the foundry processing and fabrication. So the coupling efficiency was initially measured close to the chip surface, and then the optical fiber was raised up at the different steps until the coupling efficiency was essentially maximized. The best performance we found was for the fiber position at 110 micrometer above the chip, and the peak coupling efficiency was minus 2.5 dB per coupler. So in our work in recent years, we also exploit the opportunity to address the disadvantages of native silicon nitride grating couplers, and for this reason, we exploit the hybrid platform that combine high index material which is positioned on top of the silicon nitride platform. In this case, our high index material is amorphous silicon, and it's worth to highlight that all the gratings we develop are made directly in this high index material, and the interconnected and the underlying silicon nitride waveguides serve just for light routing and not for coupling. In the first design, which is shown here, is basically the same metamaterial engineered focalized grating coupler, but as I mentioned, the grating is fully implemented in the high index amorphous silicon layer. This has a direct benefit that high index material can break the vertical symmetry of the grating, so we can have asymmetrical radiation towards the fiber, and we can achieve with this design very high directionality, close to 93%. By engineering the near field through the SWG and duty cycle apodization combined with the beam focalization in our hybrid silicon nitride grating couplers, in their apodized version, we can achieve theoretically very nice coupling efficiency down to -1 dB, which is practically very attractive. So in collaboration with the University of Southampton, this kind of surface grating couplers were already fabricated, and we also have preliminary results. Experimentally, it was measured that this kind of surface grating couplers can have coupling efficiency down to -1.7 dB, which is only 0.7 dB higher compared to our design prediction. So last design I would like to show is our uniform hybrid silicon nitride grating coupler that leverage mode interference effect. I don't want to go in much details, but essentially in the first step, the grating design is treated as a vertical virtual directional coupler, which properties are optimized through the grating parameters and through the thicknesses of the buffer layer and amorphous silicon layer. By adjusting the position between the silicon nitride waveguide and the top layer of the virtual directional coupler, we can essentially match the fiber mode to the first oscillation lobe of our virtual directional coupler, which essentially means we can internally apodize the grating. When we translate this concept to the real grating coupler with diffraction grating, and we optimize the parameters like the buffer layer and the amorphous silicon, the period and the duty cycle, we can see that we can achieve a very nice field overlap between the outradiated grating field and the standard optical Gaussian-like optical fiber mode without needing any apodization, and we can still keep very large minimum feature sizes of the grating. Initial design we published in Optic Letters. We designed for wavelength of 0.95 micrometer, and the predicted coupling performance was about -1.3 dB, which is super nice for simple, compact, and uniform surface grating coupler. In collaboration with University of Southampton, again, we fabricated also this kind of grating couplers, which in this case also implement the SWG structure. And as you can see, first experimental results are very promising, and we have coupling losses between the fiber and this kind of grating couplers of about 2.5 dB. With this, I would like to enclose my presentation. I would like to thank our collaborators and our funding. So thank you very much.